In this second part of the video on confidence intervals, we will go together through 5 different examples. Each one is relative to one of the first 5 cases in the confidence interval awesome ultimate scheme, the CHAOS. You will find an R script with all the calculations that were carried over throughout the examples. Enjoy! We will now go through 5 different exercises relative to 5 of the cases in the CHAOS scheme, that is the confidence interval awesome ultimate scheme. So exercise 1. Let me read it for you. A college admissions officer for an MBA program has determined that historically applicants have undergraduate grade point averages that are normally distributed with standard deviation 0.45. From a random sample of 25 applications from the current year, the sample mean grade point average is 2.90. So in this case, we are dealing with a normal population, mu sigma square. Sigma, in this case, is given. So we know that the averages are distributed according to a certain normal distribution. We don't know the mean, but we do know that the standard deviation, so sigma and not sigma square, is 0.45. The number of applicants is 25, and the sample mean of these grade point averages is 2.90. Right? So clearly this is case 1 from the confidence interval also ultimate scheme. The first question is find a 95% confidence interval for the population mean, right? So exactly case 1 from CHAOS. Why? Because we have a normally distributed population and the standard deviation or the variance is known. 1 minus alpha in this case, so the level of confidence is 95% and alpha is 0.05. So a confidence interval with confidence 0.95 is given by the scheme, so it's like x bar plus or minus z alpha over 2, so this will be 0.025 times sigma over square root of n. So the proofs of all these confidence intervals are given in the slides and in the videos that Marina did. So you can have a look at those videos to have like the theoretical background to get to those intervals. We just like use the formulas to solve these exercises. Everything is given in this case, sigma square root of n, which is 5, x bar. The only thing that's missing is z 0.025. So the quantity z 0.025 is the value such that a standard normal distribution, capital Z, we can call it like that, so the probability that this standard normal distribution is greater than 0.025, it's exactly 0.025. So let me repeat this because it's very important. We need to find, but it will be straightforward, the z number z alpha over 2 such that the probability, the area on the right of this value is exactly alpha over 2, that in this case is 0.025. The R command to get this is z, so to get z 0.025 is q norm 0.025 lower tail equal false. Indeed, we are looking at the right tail, so the upper tail of the distribution. So in practice, right, this is this corresponds to a quantile. This is the 0.975 quantile of a normal distribution. These considerations are not necessary for the exercise, but it's just like to make everything clear. Recall that to calculate the quantile of a normal distribution or a standard normal, we could equivalently write Q norm 0.975. So these two R commands are equivalent. Okay, great. So you have all the numbers to compute this confidence interval, right? This sigma is given, square root of n is given, the sample mean is given as well, and we found this. We can find the quantile through the RStudio function, R function. After we have done the calculation, we can find that C095 it's equal to 2.72 3.08. Of course, calculations are rather easy at this point. However, if you want to check your R codes, there's a script available with all the calculations required to solve these exercises, so you can double check that all the calculations are correct. Okay, the second part is a bit more challenging. Let's read it. Based on the sample results, okay, a statistician, so another statistician, computes for the population mean a confidence interval extending from 2.81 to 2.99. Find the confidence level associated with this interval. Great. So we have that a different statistician has computed a confidence interval as well. Now, of course, if this statistician had used the same confidence level, 0.95, they would have got the same result. So they must have used a different confidence level. And for this confidence level, they got 2.81 and 2.99. Okay? So, of course, so we need to find this beta, this alternative confidence level that they've used. So, of course, we've seen that the confidence interval in this case is centered at x bar equal 2.9, right? Right. So the confidence interval that we are dealing with, C1 minus b, will have the form x bar minus 0.09 x bar plus 0.09, right? It's a confidence interval that has to be centered 2.9, and of course, therefore, it's x bar plus or minus this quantity, which is called, okay, margin of error, okay? So margin of error. Again, you don't need to remember this, but like everything makes a lot of sense for confidence interval centered at a certain point estimate, but with a certain margin of error. So because of how these confidence intervals are defined, so if you look back here, right, so the margin of error is exactly this quantity, z 0.025 times sigma over square root of n. Therefore, in this case, we have that our margin of error, ME, which is 0.09, must be equal to z of alpha over 2, but they are using a different confidence and therefore a different significance. So this is beta over 2 sigma over the square root of n. This has to be equal to 0.09. I've already written that. So rearranging these terms, we have that the z beta over 2 will be equal to 0.09 times square root of n over sigma. It has to be like that, right? And if you solve this calculation, this is exactly equal to 1. Great, so we know that z b over 2 is equal 1. But how can we retrieve beta? Well, let's look at this representation. Okay, it's not very straight. Okay, now it is. Okay, so if we plot a Gaussian density, we know that z beta over 2 it's equal to 1. Okay, we know that this area here is beta over 2, right? So in order to find what b is, just because beta over 2 is equal to the probability that z, which is a normal distribution, is greater than 1, then I simply have that I can simply compute beta as 2 times the probability that a normal distribution is higher than 1. So don't forget the lower tail equal false. Okay, that gives me the area below the right tail. Okay, so here we are calculating probabilities and not quantize, and this is the formula to do that in R, the code to do that in R, and we get a beta equal 31.7%. That corresponds to a confidence level of 68.2%. Okay, so the confidence interval from this statistician is much, or rather narrower than ours. Okay, so because the interval is narrower, the confidence with which they can say that the mean of this population is inside this narrower interval is lower. Okay, so this is the first case from Chow's. So let's move on to exercise 2. Let me read it for you. A random sample of 174 college students was asked to indicate the number of hours per week that they surfed the internet for either personal information or material for a class assignment. The sample mean response was 6.06 hours and the sample standard deviation was 1.43. Based on these results, a confidence interval extending from 5.96 to 6.16 was calculated for the population mean. Find the confidence level of this interval. So this is similar to the previous exercise, point B. Many times you will be asked to calculate confidence intervals. However, in these exercises, there's a slightly higher difficulty because you don't have to calculate the confidence interval. You have to find the confidence of a given confidence interval. So in this case, we have a sample contains 174 individuals. We assume that these individuals, so the time they spend on the internet, is normally distributed mu and sigma square. However, this time the standard deviation and the variance is unknown. Okay, and indeed we are told here that we only have a sample standard deviation. That's not the real standard deviation of the population, it's only a sample standard deviation. So the sample mean is equal to 6.06 and the sample standard deviation, so this is not s squared, is s unsquared, is 1.43. Okay, so clearly this is case 2 from Chow's, our ultimate scheme. In this case, with the second case from Chow's, this is about a confidence interval on the population mean, right, when the variance is not provided. This will be a confidence interval centered around the sample mean plus or minus, and the confidence interval, that the margin of error, right, of this confidence interval is depends on a student t-distribution. Depends on a student t-distribution, and now we'll look at the code to compute this, although I believe you already got it right. So, well, let me remind you, like in this is called the margin of error. Okay, just a way to call it, not very important. So, In this case, the confidence interval is 6.06 plus or minus 0.1. It has to be symmetric around the sample mean. And indeed, in this case, it's 5.96, right? Well, let me repeat it. 5.96 and 6.16. So same notation to indicate the same confidence interval. Therefore, the margin of error, which is T alpha over 2 S over square root of n, has to be equal 0.1. It's enough, okay, it will be easy enough to just rearrange these terms to find that T alpha over 2 is equal to 0.1 square root of n over S, okay? And therefore, if you solve these calculations, you have that T alpha over 2 is 0.925, okay? Now we need to find alpha. So we know that alpha over 2 is the probability, okay? So very similar to the previous exercise point B. So have a look at the picture we drew back then. But we know that alpha over 2 has to be the probability that a t-distribution, right, with n minus 1 degrees of freedom is higher than 0.925. Okay, so you can compute these in a straightforward way. We have that alpha will be equal to 2 times, okay, and this is the pt, right, of 0.925. Degrees of freedom are equal n minus 1, n is 174, so this is 173, okay, and lower tail is equal to this, resulting 0.356, right? So very similar to the exercise before. Only thing like we need to be careful about is the degrees of freedom, right, of this student team, right? So if we know the variance of this normally distributed population, then this will be a z-score. If we don't know the variance, right, so if we don't know the variance, then this will be a t-score, but the t-score depends on the degrees of freedom, and the degrees of freedom will be, so if you look back at the pivotal quantity, the degrees of freedom of the corresponding pivotal quantity is n minus 1. So case number 2 from Chau's solved. Let's go on with exercise 3. Great. A manufacturer is concerned about the variability of the levels of impurity contained in consignments of raw material from a supplier. A random sample of n equal 15 consignments showed a standard deviation of 2.36 in the concentration of impurity levels. So with this phrasing, a random sample showed a standard deviation. Here, what is intended is that the sample standard deviation is 2.36. We can assume normality. And therefore, here we have that our population is normally distributed. This is one of the assumptions. We don't know the mean, unknown, all right? And of course, we don't know the variance either, but in particular, we want to calculate a 95% confidence interval for the population variance. So this is clearly case 3 from Chau's. All right, so we're interested in this confidence interval around the population variance that we don't know. Okay, so this is point A. Going back to the Chau scheme, we know that a confidence interval with confidence 0.95, this is what we asked for, will be n minus 1, right, s, so sample variance squared, over chi square 1 minus alpha over 2 with n minus 1 degrees of freedom. And recall, this is the only one of our cases where the confidence interval is not symmetric around the point estimate, and the the right end of this interval will be chi square alpha over 2 and minus 1. Great. So we already have most of the, well, we have everything right. We just need to square the sample standard deviation and we are done. So this is a simple task to do, compute the confidence interval with respect to the previous exercises. The only thing where we need that we have to double check is how to compute this, right? However, that's very easy. So chi square alpha over 2 n minus 1 can be computed with the command, let me think about it. So this is a quantile, it will be a quantile of a chi square, right, with so alpha is 0.5, so alpha 0.05, sorry, so alpha over 2 will be 0.025, and the degrees of freedom will be 14, right? And of course we want the lower tail to be false. Okay, and the result from this calculation, you have your script to find it, so not difficult, will be 26.12. To find the other extreme of the interval, you need to retrieve this quantity, but it's all, everything is very similar. So this is q chi square, 0.975 this time, degrees of freedom 14, and lower tail equal false. And this will be a much lower value, in particular 5.63. Great. So if we combine this information with the s square and n minus 1, you have a confidence, the resulting confidence interval will be equal to Ci 0.95. It's equal to 2.98, so you can double check all the calculations, and 13.85. So point number B of this exercise, you don't need any calculation, so you can double check, but you don't need any calculation to do it. Would a 99% confidence interval for this variable be wider or narrower than that found in part A? So if the confidence is higher, so if we want to be more confident that the parameter sigma square will be between, will be inside our interval, then the confidence interval will be wider, right? So higher confidence will result in a wider interval. In particular, we can double check this result. So if you want to be 99% sure that our confidence interval will contain our estimate, let me just redo the calculation very quickly. So the resulting confidence interval is well, slightly wider. So you can try and calculate this with the same method, and it's 2.49 and 19.14. So a wider interval, that's because the confidence is higher. So to be even more sure that our interval will contain the parameter sigma square, well, we need to have a wider interval with respect to the one we had before. And this concludes our third exercise. Exercise number 4. Okay, for this exercise, well, for this case, I've included 2 exercises. The first is slightly easier, so you can try that by yourself. Let's go through the second one. A research group wants to estimate the proportion of consumers who plan to buy a scanner for their PC during the next 3 months. How many people should be sampled so that the sampling error is at most 0.04 with a 90% confidence interval? Okay, so let's analyze the setting of this question. So we want to find a confidence interval for the portion of population, the population portion that will buy this scanner. So we want a confidence interval for our population proportion P. So we know that the population is Bernoulli distributed. People will either buy or not buy a new scanner. We will assume that n is big enough. Okay, so that this result, which is asymptotic, holds. So, well, when it's about the population proportion, for our course, the only case that we've looked at is case 3 from Chaus. Okay, so in particular, we are asked the number of people that have to be sampled in order for the sampling error of a 90% confidence interval to be 0.04. Okay, let's look at this carefully. So we want to calculate a confidence interval with confidence 0.90, right? This interval will have this kind of shape. This will be p hat plus or minus a z-score, z 0.05. Recall that here we have alpha over 2. Alpha is 0.1, 0.1 divided by 2 is 0.05. Plus or minus, you can look back at your at the Chaus scheme, p hat 1 minus p hat over square root of n. And so this is the kind of confidence interval that we're looking at, and we want the sampling error to be at most 0.04. That the sampling error is a different name for the margin of error. Okay, so sampling error is just the margin of error. Margin of error that we have called before. So which is this one. Okay, so the margin of error, which is z0.005 square root of p hat 1 minus p hat over square root of n, has to be lower than 0.04. Okay, so this question is tricky. This question is tricky because, like, we don't have access to our p hat. This is really the most difficult thing that can happen. However, with a simple trick, we can actually solve this. How can we be sure that this thing is lower than 0.04? So we know z.0.05, but we don't know p hat, right? Because we haven't sampled we haven't collected a sample from these individuals yet. However, we know so if p hat will always be between 1 and 0, right? So consider the function p hat 1 minus p hat. Okay, this is always lower than 0.25, right? So you can check this carefully, but actually we can do it together. So if you look at the function of p hat, which is equal to p hat 1 minus p hat, if we calculate the derivatives very quickly, right, we have that the derivative is 1 minus, let me check, p square, so minus 2p square, okay? So the derivative is equal to 0 if and only if pi hat is equal to 0.5, right? Yes, correct. And therefore, the derivative evaluated at 0.5, it's equal to 0.25. So really, if you study the second derivative, so we can do this, the second derivative is equal to minus 2, so it's always negative, so definitely this is a maximum, okay? In this point, p hat times 1 minus p hat is a maximum. Therefore, p hat times 1 minus p hat will always be lower than the maximum achieved by this function, which is achieved in 0.25, okay? So, going back to our problem, NE, the margin of error, which is 0.05 square root of pi 1 minus pi hat square root of n, is always lower than 0.05 square root of, and the minimum, 0.25 over a square root of n. And this has to be, and we will set this to 0.04. So in this way, we are sure that the margin of error is lower than 0.04. And now, the only quantity that is missing is n, right? And we can rearrange the term, okay, to get that n has to be equal to z 0.05 times square root of 0.25 over 0.04. And the result of this calculation will give 423. Okay. I'll let the remaining part to you, right? You only have to play around with the level of significance, or equivalently the level of confidence, but intuitively, what is the sample size required if the confidence is increased to 95%? So if you want to be more sure, we will need to sample more people if you want the same margin of error. So if you repeat these calculations, you will find that in this case n is equal to 601. And in point C, okay, again, you can do that, so I'll leave this to you because it's the same procedure but with slightly different calculations. So this time we want the required sample size if the research group extends the sampling error to 0.05. So now this upper limit, right, upper bound is a bit more generous, okay? However, the confidence has to be 98%. So even higher confidence than 95%. And the result, have a go at this exercise, is 542. And this is exercise, this is case, sorry, I wrote case 3, but this is indeed case 4 from Chaus. This fourth case contains 2 exercises. The first one is more standard, easier. This second one is a bit more challenging. So this is why I decided to go through this one. Last exercise, we are getting there. Exercise 5. Okay. This is not difficult, it's just to give you an example of what a question about this last case can look like. Suppose that for a random sample of 200 firms, okay, let me write the data while we're reading it, that revalue the fixed assets, the mean ratio of debt to tangible assets was 0.517. So we are measuring this financial ratio, which is the ratio of debt to tangible assets, and we measured these 200 firms, and the ratio was 0.517. So the sample mean of the ratios for this population of companies. And the sample standard deviation was Sx. So I'm anticipating that there are two different populations of companies, is 148. Great. For an independent random sample of 400 firms that did not revalue the fixed assets, so we have a different samples with a different number of firms, companies. However, they didn't revalue the fixed asset, so a different evaluation of the fixed assets. And for the average, the mean ratio of debt to tangible assets for this second group of company was 0.489, and the sample standard deviation was 0.158. Find a 99% confidence interval, right, for the difference between the two population means. Assume that the two populations have equal variances. So we know that the two populations, we are assuming that these two populations have equal variances. Therefore, this is clearly case 5 from the Chaus scheme. Great. So we have two populations, different population mean, same population variances. However, the sample variances can be different, right? Because they depend on the sample. So the confidence interval with confidence 99% will be equal to, if you look back at the scheme, you will have that is centered at D bar, plus or minus student T with here alpha over 2 is 0.005, okay, half of 1 percentage point, and we have to calculate the square root of the pool sample variance over nx, yes, the pool sample variance over ny. Okay, so this is the resulting confidence interval. Very important, very important to compute. So let me first compute this one. So to compute this quantity, right, this is 0.05. However, we also need to compute this quantile, the degrees of freedom, and the degrees of freedom is nx plus ny minus 2. So the command to compute this is qt, the quantile of a t student distribution, evaluated at 0.05. The degrees of freedom will be equal to nx plus ny minus 2, but we want the right tail, so lower tail equal false. Okay, so you can double check the calculation. And the other thing we need to be careful of is to compute, so a bit annoying, but we are done. So nx minus 1 sx square plus ny minus 1 sy square over nx plus ny minus 2. This is the sample pool variance. So you have all the calculations on the script that I've shared with you. So I'm checking just like very quickly. This should be around 2.58. You have that, you can compute the sample variance accordingly, and you should get 0.024, right? And of course, if you feel very important, but I'm sure that you got this already. So d bar is defined as the difference between the two population means, right? So in this case, this will only be right, x bar minus y bar, right, which is equal to 0.028. And then if you feel the missing dots, you will get the corresponding confidence interval, which is so confidence interval 99%. Okay, it should be minus 0.0066 or 67, just like to round it more, 0.626. Okay, so this exercise is more just plugging in numbers. However, look at this confidence interval that we get, right? 99% confidence. So this is the mean ratio, this is the ratio of debt to tangible assets, right? So it seems higher for those people who did revalue the fixed asset. So the ratio of debt to tangible asset seems to be higher, So basically, it seems like revaluating the assets have caused a decrease probably in the asset value with respect to not revaluating them, right? Because like the debt to fixed asset ratio has gone up. However, can we be sure that really in the population the debt to tangible asset ratio is higher for companies who have revaluated their asset? Well, we know that the difference between the difference D, which is the difference between x, mu x and mu x and mu y. Okay, so we have a confidence interval for this quantity, which is between minus 0.0067 and plus 0.0626. So it seems like it's probable that mu x is higher than mu y. However, this interval contains 0. So it's also possible that the difference between these two population means is 0. Okay, if you're thinking about with 99% confidence, we know that the population mean is inside this interval that contains 0. Therefore, with 99% confidence, we can't be sure that the difference is positive. It might be negative. However, if we decrease 99% to 95%, probably we will get a positive confidence interval. So, for example, with 95% confidence, we could say, okay, 95% confident, we could say that D, which is equal mu x minus mu y, is higher than 0, so that this difference is positive. Okay, now this will disappear. Okay, no problem. So about this last exercise, I hope that the calculations are clear, very important, but also the rationale and how to interpret our result. This will be particularly important, like this interpretation, when we start, okay, with hypothesis testing. So I hope you find these, the scheme and the associated exercises useful. I hope most of the things are clear, and of course, if anything is unclear, get in touch, and I'm always happy to provide help and support. So see you in the next video. Bye!